How do we prove that a new medication actually works? That's a key question for scientists to solve. And really, what it comes down to is the way we use statistics to understand the data. Suppose a researcher's developed a new medication and they want to test it out in the clinic. How will they tell if the difference between the groups is enough to say that the medication's actually working? Now, if you do a study like that and 100% of the people who took the new medication show a response to it or are cured, that would be a pretty clear signal. But oftentimes in the real world, things just don't work out that way. Often what you'll see is that there are people who in the placebo group respond very well, even though they just got a sugar pill that doesn't do anything. And you'll have people in the medication group who, if the drug actually works, may show a strong benefit, but others who don't respond at all. So where do you draw the line to say that a medication is actually working or has enough of a benefit that it should go forward in more studies or actually be taken to patients in the real world? So that's where statistics come in. And for the purposes of this video, I'm not going to try to dig into all the underlying math. It's pretty complicated. I don't even understand all of it. But what I would like to do is help folks understand at a fundamental level when a scientist is saying that something, a result is significant or statistically significant, what does that actually mean? The fundamental concept is that when we do an experiment and we collect data, as scientists, we approach that data as an estimate of the true value. So just to give you an example, if we think about what is the average height of all humans on Earth, there's a correct answer. If we were able to measure everybody, we could get that answer. But even then, there would be error, for example, in how we measure it in terms of the yardstick that we use. People's heights also change over time. And so that number will change. So we can't realistically get that. What we can do is collect a sample. Say we measure the heights of 3,000 people from all around the world, and it gives us an estimate. Now, if we do that 100 times, those estimates will not all be exactly the same, but what we expect would happen is they would all kind of fall around the true value. And it would follow a pattern such that most of the estimates would be close to the true value, and some of them would be farther away from it. And so we have a lower probability of having estimates that are far away from the true value. So if we apply this line of thinking back to the case of the clinical study, what we're really getting is two different estimates of an effect size. The effect size in the placebo group and the effect size in the new medication group. And the question we're asking is, are those two estimates taken from that same distribution or that same pattern, or are they actually different from one another? Now, what we do mathematically is we calculate the probability using some underlying assumptions that those two estimates are taken from that same distribution, that same pattern, or not. And then as a community, we have to apply a threshold to say, okay, well, at what probability are we going to say that this is a real result versus something that's just, okay, you just by chance had two different values that were different from one another. Collectively, the scientific community has landed on 5% as that threshold. So the way that it works is if we calculate that there's less than a 5% chance that those two estimates were taken from the same distribution, we're going to say that they're different. If it's 5% or more, we're going to say that it is not significantly different. This is not a perfect solution, and it can lead to some strange conclusions. Say you have a result that's a 4% probability and one that's a 6% probability. Intuitively, to us as humans, that's not that different of a result. But because of this convention of having a threshold of 5%, one of those will get reported as a significant result. The other one will either never get reported or will get reported as not a result at all, not a significant difference. There has been a trend towards researchers just publishing that probability directly rather than relying on a threshold so much. But the concept of this 5% threshold for statistical significance has held really strong in scientific discourse, and I don't see that changing anytime soon. Now, there are other statistical approaches that can work a little bit more like the way we as individuals or as humans think about data. For example, they can take into account prior information. Say this is the 4th time you've done that experiment, and all of the other 3 times there was an effect. And now, on this last experiment, you find that there's a 6% probability, so it gets thrown out. Well, these other methods would allow you to take into account that prior information and weight that more heavily, kind of how we would think about it as human beings. Those statistical methods are established, they exist in the literature, but they're difficult to apply, and not many researchers really understand them all that well. So that kind of approach hasn't taken a strong foothold in the scientific community and how we think about analyzing data. And I don't really think that's likely to change given those constraints and how tightly ingrained that probability threshold of 5% is for the scientific community. The take home from this is that when you do experiments, data can be messy and noisy. And as scientists, we really rely on statistical methods to help us figure out where do we draw the line to say that some effect is real and meaningful and when is it not. It is not a perfect system. It can lead to strange biases and to changes in reporting, some results never getting reported at all because they're called non-significant, other results getting reported because they have a very, very low probability, even if that result is not really all that meaningful clinically. So it isn't a perfect system, but it does provide us a consistent framework for thinking about data and thinking about how an effect can be meaningful versus just noise, and preventing us from just arguing with each other about whether a result means something or not. If you found this interesting, I'd really appreciate if you could like, subscribe, or let me know in the comments what you're curious about in terms of how scientists approach data and make sense of all of this stuff that they're collecting. With that, thank you for watching, and I hope you have a great day.